You should have finished the second web-assigned homework. There's also a paper homework that's up. It's on the class schedule webpage, so that's where they will always be. If you've had trouble getting into WebAssign, please first try and contact them, and then let me know, and I will yell at them. I know some people have trouble. I don't know. Any other questions? Okay. Also, if you're having, if when you look at your WebAssign, I think it's problem 9 on homework 2 in particular has some issues with the grading. I don't remember the answer, so I'm going to write something wrong. I think it's number 9. I don't think it's a sign. But if the correct answer is something like, I don't know, 1/2 sine cubed of x, it takes an answer written this way, and it does not take an answer written this way for some reason. I complained to WebAssign about it. They're going to fix it, but it's already out there. So if you got burnt by this and lost points, click on the Ask Your Teacher link and get it fixed. I think it's number 9. Does anyone know? The answer is really something like a cotangent or a cosecant or a secant. Does anyone know? Yeah.
Well, I tried writing something just like that, but you put a parenthesis around the sine and the x, like the bigger one,
Yeah.
and then put it to the third power, or what?
Yeah, well, so all of them should take this, or this, or this. But one of them, it's either number 5 or number 9, I think it's number 9, doesn't take this. And if you put this in, it gets marked wrong. If you change it to this, it gets right. So if you put it in like this, and it gets marked wrong, and you change to this, and it gets marked right, click on the Ask Your Teacher and say, WebAssign was dumb on this problem. Please give me my half a point back. So that we know. Because the point is not to rob you for notation. The point is to know whether you can do the problem. So the only problem that I know of is that one. All the other ones will take any of those 3 formats. Okay. Here it is. Okay, so where we were is we were doing integration by parts, which is useful when you have, it's a way of trading derivatives for integrals. So if we have something, well, let me just, yeah. So, okay. Let me do one more example. Let's say the integral from, let's make it a definite integral this time. No? Okay. I feel like Obama when the guy shouts out, "You lie!" We don't know that. Okay. Whatever. Let's do something like this, 0 to the power of 4. It's not a perfect way. So suppose I want to do this integral. There's actually several ways I can do this integral. One way I can do it, so should I use parts on this? Yes? What should I take for the parts? Take one part for sine x and take the other part for sine x? Okay. So that means that du is the cosine and v is minus the cosine. So that gives me minus, did I do that right? Yes. Minus sine x cosine x from 0 to pi over 4 minus the integral of v du. Oops. Geez. So I think I did that right so far. And this is from 0 to pi over 4. And this is So the sine of pi over 4 is root 2 over, yeah?
Can you just use a half angle identity?
Well, that's the other way. So you can do it by parts or you can do it by using a half angle identity. Either way is fine. So let's do it by parts though, because they wanted to do it by parts. So the sine of pi over 4 is root 2 over 2. Cosine of pi over 4 is root 2 over 2. So this is minus the sine of 0 is 0, cosine of 0 is 1, so that part's gone. And then I have to do the integral of cosine squared. Now if I do the integral of cosine squared, I could do it by parts again. But in fact, it's easier to remember a different identity. So I think if I do it by parts again, I get stuck. Pretty sure I get back to the original integral if I do it by parts again. I get 0 equals 0 or something like that. So that's not going to work. Feel free to try it, but I'm pretty sure it doesn't work. So I have to use the fact to do this. What is another way I can write cosine squared? Yeah?
1 minus sine squared.
Right. So remember that sine squared plus cosine squared is 1. And so this becomes the integral from 0 to pi over 4 of 1 minus the sine squared. And now again we're in one of these tricks. Yes, we're in one of these tricks where I'm going to get the integral sort of related to itself. So this is 2 over 4, so this is a half from here. This is the integral from 0 to pi over 4 of dx minus the integral from 0 to pi over 4 of the sine squared. And that equals the integral from 0 to pi over 4 of the sine squared. So I have a thing that I don't know equals to a number plus something I can do easily minus the same thing. So that means, come on, go up there. So that means I can bring this and add it to this to get 2 times the integral from 0 to pi over 4 of the sine squared equal to a half. Did I use the sign something? Negative a half plus, well, the integral from 0 to pi over 4 of dx is x from 0 to pi over 4. So that means, so this is pi over 4 minus a half equals twice the integral I want. So the integral I want is pi over 8 minus a quarter. Or pi minus 2 over 8. Which is a little bigger than 8. Okay? So there's two things going on here in this example. One, I'm doing an integration by parts, which is a definite integral. And one of the things that you can do, you don't have to, you can go all the way to the end and then plug in, is that you can plug in as you go and get rid of some of the parts. So that's what I did here. The other thing is, if I had tried to do this cosine squared the same way I did the sine squared, I would actually wind up with 0 equals 0, so that doesn't work. So sometimes, when you do integration by parts, you wind up with something, it's true, 0 does equal 0, but you wind up with something that doesn't really get you anywhere. So this is true of integration in general. Going backwards is often harder than going forward. I mean, trying to an art in figuring out how to do this. I wouldn't call it art. It takes perseverance. Okay, so I'm going to stop with doing integration by parts right now. because I'm tired of it and we have to move along because we're still behind from the hurricane. So, but as somebody else noted, I could also do this integral by using, well, let me do the easy ones first. So suppose instead of that, I had something like the integral of sine cubed of x dx. And let's just make it an indefinite integral this time. And let's make it easier. Let me throw a cosine in there. Make it easy. So say I have an integral like this. What would I do? So I hear people mumbling substitution. Factor the sign off. Yeah? So why would I do that? Just because I can? Okay. I mean, this is true. I don't know that it helps. So what these other people are shouting out is true. Let's make a substitution. I mean, I can do this, but I don't want to. So let's make a substitution. What should I substitute? I hear a bunch of mumbles. Okay. So I should substitute sine. Why should I substitute sine? Because the derivative is sitting right here. So I make the substitution. Just so you don't call it U substitution, I'm going to make the substitution W equals sine of x. And that's good because right there is my dw. And so when I make that substitution, that makes this a really easy integral. And so then this is just 1/4 W to the fourth, and W was the sine. So let me point out something that students always do because they think it's quicker. It's really important that we write things down that it's true. Especially in something like this. Notice that everything I wrote equals the previous thing. And I wrote equals every time. And I didn't leave off bits until the end. It's important, even though it makes you sound like I'm trying to be an evil accountant or something, that you keep track of all of the bits. Because you need them later. And so, rather than just writing stuff all over the place, try and write it in order and make sure every stage is equal. When you write equals, it means the same. It doesn't mean becomes. Equals means equals. It means the same. If something becomes something else, don't write an equal sign. Also, don't write arrow when you mean equal. I see a lot of students that would write, this, arrow this, arrow this. Now in this case, it doesn't matter whether you think of equal as a process that gives an outcome. It just is true if we just say this equals that, and this equals that. Don't write equals if it's not equal, because then you get in trouble. You don't get in trouble for me, you get in trouble because you wrote garbage. And eventually you get confused. Sorry, that was a little off to the side tirade. I see it all the time in calculus, that students just write junk all over the page and then magically the answer appears. And that's fine if your junk has no mistakes. But if you make a mistake, we can't find it, so we can't give you partial credit, and also you're less likely to make mistakes and proceed in an orderly fashion. If you're going to write junk all over the page, write it on another page, and then put it together. Okay, I lost track of where I was going because I had to rant for a minute. There we go. All right, so this is actually a general trick. When we see an integral with a pile of sines and one cosine laying around, it's easy. And when we see an integral with a pile of cosines and one sine laying around, it's easy. So if we had an integral like sine to the fifth of x cosine squared of x dx. Let's make it sine cubed. Let's make it easier. Suppose I have, it didn't really matter. What am I doing? Yeah, suppose I have something like sine cubed of x cosine squared of x dx. I'm going to make a substitution. So I'm going to make this a quicker question. Some stuff. Okay, so choices are make some manipulations and then make the substitution u equals sine. Make some manipulations and then make the substitution u equals cosine. You can do either one and get the answer, or no, this is a bad idea, just go away. So I started two questions now. So most of the people think we should manipulate it and then substitute the sign. Okay, so let's see. What manipulation should I make? Those of you that think we should do a manipulation and then substitute the sign. Since 57% of you think that's what I should do, maybe at least one of you knows what I should do. Yeah?
Have a u equals sine cubed, and then just take the derivative of sine cubed to make sine cosine squared, and some other stuff.
So you're saying u equals sine cubed du is then cosine squared x sine x dx. Wait a minute, what am I doing? Sorry, I'm hallucinating. Okay. 3 sine squared x. What? Well, he said cube. So cube isn't going to work because now I have an extra business. This is a bad idea. U equals sine squared. So then du is 2 sine x cosine x. Hey, that one works. No, it doesn't. Okay, so if I do that, so then that integral becomes well, I have u, then I have a sine x cosine squared x dx. One of those is du. So this is u sine x cosine x du. And I don't know what to do with that. I guess this could be a square root of u, but this guy is still there. So this doesn't work so well either. Yeah. You in the back.
I think that cosine x squared equals 1 minus sine x squared.
Okay. I guess I'll go over here. So here I'm going to use the fact that cosine squared is 1 minus sine squared. And then?
Just go on.
What?
Then it should be sine x to the third minus sine x to the fifth.
Okay, I can do that. And then?
Then it should be the sine x to the third integration minus the integration
Yeah,
of
okay,
sine.
but I still can't do these integrals. Oops. And I'm still stuck. I don't know how to do either of those integrals.
You use u equals sine x.
Okay, let's just take this one.
Yeah, sine x.
So now I don't know. I mean, I'm not trying to make fun of you. I'm trying to point out there is something going on here, and if I just tell you, you're going to forget. So, anybody else? So this is a great idea, except it's a little bit wrong. Yeah? So, right, so peel off two of the sines and turn them into cosines. So this is a bad idea too. No, that's a good idea. Okay, so this is close, and as he said, instead of focusing on trying to turn the cosine into sines, let's turn most of the sines into cosines. So write this integral as sine x, that I'm just going to save for later because I might get hungry. And then I have sine cubed, sine squared of x, cosine squared of x, dx. So it's the same, but this is 1 minus cosine squared. So now this becomes, I'm going to write the sign at the end, 1, or how about cosine squared of x minus cosine of the fourth of x times the sine of x dx. And now I'm happy, because when I eat these cosines, I have the sine left over for dessert. I can let u be the cosine, and so du is minus the sine that I need. This becomes negative du. And this becomes u squared minus u to the fourth, which I can do, which is easy. So let me just finish. So now I get, I lost my place, the integral of u squared minus u to the fourth du, the whole thing negative, which is negative u cubed over 3 minus u5 over 5, which is, let me rewrite it in the other order, u is cosine. Cosine to the fifth minus cosine cubed plus a constant. So that means that this choice for sure works. And I don't know how to make this one work. And so if A doesn't work, neither does C. Okay. So this is a general procedure. Whenever I have an odd power of a trig function laying around, so in general, if I have the integral of sine to the m, cosine to the n, then if either one of these are odd, let me just say if n is odd, then I convert all but one sine into cosines by sine squared is 1 minus cosine squared. I didn't leave enough room. If n is odd, then I do the same thing, but I convert sines into cosine by the other piece. And if they're both odd, I can do it either way. So this answer is sort of right in spirit, but it depends on which power is odd and which power is even. Yeah?
Does it matter if n is greater than n?
Don't care. It can be negative too. So the trick is that I want to have laying around. So what I want is the integral of stuff in sine. Let me just call it a function of sine. Times a cosine x dx, or some other function of cosines times sine x dx. I want everything except one of them to be the other guy. And then this becomes easy. It's a straightforward substitution. Away we go. So the thing to remember is not memorize this formula, but just remember that you know the most useful trig identity is not even trig, it's the Pythagorean theorem. Well, it's the same thing. This identity if you learn one thing from trig, it should be that. I hope you learn more than one thing from trig, but that's the one thing that is most important from trig, which is just the Pythagorean theorem. So using that trick, we can always get rid of all but one of an odd power. Okay? Running a little low on time. Let me not do another one of those at the moment. You get to do some on the homework. What case did I miss here? Did I stop this? If they're both even. If they're both even, like the integral that I did at the beginning, or, well, let's just do that one. So here, the power of the cosine is 0. That's an even number. And the power of the sine is 2. That's an even number. I can't use this trick. Because if I take one sine away, and if I turn both sines into cosine, I'm in the same creep that I was in before. And if I don't do it, well, then I have no hope. So I can't use that trick. And I always forget which is plus and which is minus. So I have to use a different trig identity. So I want to use either this identity or this identity, which maybe you remember and maybe you don't. I always tend to forget them, so I can cheat, but I get to cheat. And so here I'm going to use this one. And then this integral becomes pretty easy. So this is, so I integrate 1 and I get 1/2 x, and I integrate 1/2 cosine 2x. So when I integrate cosine 2x, I get 1/2 sine x, sine 2x, and then I get another half. So this is minus 1/4. We can check that. No, not really. I mean, you can check it by taking the derivative and then using this formula to go back. Did I mess up the sign somewhere? Okay? So, if both are even, then you use this. Then we convert, we so if you have an even number n, notice what this does. This takes an even power and it turns it into half of that power. It changes the angle by a factor of 2, but it turns everything into half of that power. And so, ultimately, if you take an even number and you keep dividing by 2, unless it was 0, eventually it becomes odd, and then you can use this trick. So if I wanted to do, say, sine to the 4th, well, then I would do it twice and get down to the power of 1. So these things can be a little tedious, but, okay. So I want to put aside this business for a while. These are easy once you get the hang of them, other than sometimes there's a little bit of tedium with manipulating trig identities over and over and over again. But I'll leave that for recitation. I can use that word. Okay, so another thing that we can do related to, so what I'm trying to do right now is just go through techniques that work for various types of integrals. So related to trig identities, we have this one, sine squared plus cosine squared equals 1. Well, I guess I can use that. So if I have an integral like, now watch, I'm going to do one that doesn't work. Okay, my brain just froze. Let me see it on the board. So the problem with these is sometimes they don't, you choose one that doesn't work and then you are a creep. I didn't want to do that one. Sorry. Yeah, let's try it. So, say I have one like this. Now here, if you try substitutions, it's not going to be so good. Well, there's a right substitution you can make. The trick to notice here is actually there's some trigonometry going on here. It just doesn't look like it. Somebody said something. It's arcane. Yeah. So so the problem here is this stupid square root of x squared plus 4. And I'd like to get rid of that, and I'd like it to be like the square root that I can do. So I remember, maybe this should be a 1 to make it easier. Can I make it be a 1 to make it easier for that? Yeah. I mean, I can do it when it's 4 too, but let's do it when it's 1. So here, I remembered some trig identities. So this guy, right here. I remember this guy, which is not useful here. And I remember this guy, and this one is useful here. Tangent squared plus 1 is secant squared, which you can just get by mushing this one around. And here I have something squared plus 1 becomes a square. So that means that if this x were only a tangent, then this would become just a secant. And then I could do this integral. So let's just say, well, I wish the x were a tangent. So I'm going to let x be the tangent of some angle I don't know. Let me call it theta. And so that means that dx is the secant squared d theta. Okay, fine. And so here, by doing this, oh, I can't do this one up. I can now rewrite the integral to get, so the dx becomes the secant squared x squared becomes a tangent squared. The square root becomes a secant squared. And now I can do a little trig manipulation. So let's reduce this. The square root of secant squared is secant. So this is, let me just rewrite it slowly. So I have a secant squared on the top, pick up another secant on the bottom, and I have a tangent squared here. And so that I can keep track of everything, I mean, this is really 1 over cosine squared, this cancels this, and then you make cosine on the top, and I'll just write everything in terms of sines and cosines so that I know where I am. So the secant squared is 1 over the cosine, so I'm going to put that on the bottom. And actually, first I'm going to cancel this guy with that. So that gives me a 1 over cosine. That's from this bit. And then I'm left with, well, tangent is sine over cosine, so that gives me a cosine on the bottom and a sine on the top. Squared. So I think I did that right. Is everyone clear on where I went from here? Yeah. Okay. So this x squared plus 1 becomes the secant squared. I'm taking the square root of secant squared. Square root of something squared is just the thing. And then this secant cancels one of those secants. And then a secant on the top becomes a cosine on the bottom. This is upside down, isn't it? See, you should have told me. This is a cosine squared on the top and a sine squared on the bottom. So again, I can cancel this with that. And so, I guess I'll use this one. And so after all of that hoo-ha foo-faroo, we wind up with that I have the integral of cosine over sine squared. Well, that's one we can do. Yeah. It's on the bottom. So this is sine over cosine, but it's on the bottom, so I need cosine over sine when I bring it up. So after all of this mess, I get that. And this is easy. What do I do? U equals sine. Well, yeah, I didn't use U yet. Okay. So this guy becomes just the integral of 1 over u squared du, which is 1 over u negative, wait a minute, I need a 2? No? Yeah, that's right. But u, well, u is the sine so this is the cosecant, negative cosecant if you want, or leave it as 1 over sine, I don't care. But my question was not about theta, my question was about x. So if x is the tangent, then theta is the arctangent. So this is really the cosecant of the arctangent. But the cosecant of the arctangent has another name. So we should figure out what that is. So I want to draw a picture. I'm going to draw a right triangle, so you have to remember some trigonometry now. And I'm going to let this angle be theta. Now, if this angle is theta, x is the tangent of theta, because that was the choice I made. The tangent is the opposite over the adjacent. And I want the tangent of this angle to be x. So if this is x and this is 1, then the tangent of theta is x. That means that this hypotenuse, I use the Pythagorean theorem, is this squared plus this squared, take the square root. Now what I want is not the tangent, I want the cosecant, or 1 over the sine. Let's leave it as 1 over the sine. Cosecant is 1 over the sine. So the sine here is this over this. 1 over the sine is this over this. So this is minus x, no, that's the sine, sorry, is minus square root x squared plus 1 over x. Which seems like magic, but it's reasonable. I'm integrating some algebraic function. I do a bunch of stuff involving trigonometry, and eventually I get back to another algebraic function. So, the short of this, well, I don't know, these are never short. So what went on here is when we see the square root, or actually just something squared plus a constant, this trig identity can be helpful. And you turn it into a trigonometric integral, which then is not so bad. You do just the way I said how to do that. And then you go back. If I see something involving, for example, 1 minus x squared, I would use this identity. And if I see something involving x squared minus 1, I would use the other. Yeah. Okay, so let's look at this if this is x squared plus 4. So I won't go through the whole business. So I'm going to do exactly the same integral, but when it's x squared plus 4. Well, I'm not actually going to do the integral. I'm just going to start it. Okay, so this square plus a thing tells me that I want to use, where'd you go? The guy who asked. Okay, thanks. It helps me to look at somebody. This tells me that I want to use something like an arctan, but if I use this one, it's not going to help me. So what I want to do is divide everything by 4 and multiply back by 4. So I rewrite this, which I don't have to rewrite explicitly, but I'll rewrite it in my mind, but I'll write it explicitly so you can see my mind. As, well, I'm going to factor this 4 out. And so when I factor 4 out of here, I get x squared over 4, but I can actually write x squared over 4 as x over 2 squared. Like that. And so this is, and then I can pull this 4 all the way out. And now I have a thing squared plus 1. Now I can use this trig identity. I'm going to let x over 2 be the tangent. And then I just go from there. So I want to get rid of this squarey thing. So I get the same. Well, it isn't quite the same because this. I'll pick up some factor of 4. But it's almost the same. Okay, let me not finish this. Yeah, since it's 5, then I need a square root of 5 then. Or, doesn't, I mean, you can take the square root of any number. So if this had been, instead of a 4, how about a 41? Well, then this would be a 41. And then here, this would have to be 41 over 2. well, I want to take the square root of 41 here. So this would be square root of 41. And this would be square root of 41. And this would be square root of 41. It's the same. Now, you got square roots floating around, and yeah, okay. Yeah.
I don't understand why you divide it. Why couldn't you just have done two tangent theta instead of x over 1?
Well, it's the same. I could have done 2 tangent theta. I mean, we're here, square root 41 tangent theta equals x.
Why didn't
Same.
you divide both together? Why couldn't you just have it like that in the first place? I'm saying like it all comes up to the same, but I don't understand this.
I don't see, maybe I'm misunderstanding what you're suggesting. 2 tangent theta. So what do you mean by, so let's put it back to 4, because the 41 is just annoying. 2 is a lot easier to write. Okay, so it's a 4 again. What are you proposing I do now instead of doing this mishmash?
Because x squared plus 4 would be 2 tangent theta. Right?
No,
I mean, the square root of 2 tangent theta.
no.
Because
I have to convert it into a secant. So the trick here that I want, I mean, it is, you really have to divide by the square root. I don't know how to get around it. So I mean, if I let x be 2 tangent theta, that's okay. But that's exactly what I did here. I said let x over 2 be tangent theta. So that I could. Okay. All right. Okay, I don't have time to start the next thing. So all of these things, you use these kinds of rules. You go from there. So yeah. We'll do partial fractions on Friday.